Hello, everyone. My name is Shahriar Afkhami, and I'm a researcher from Lund University. And I'm here today to briefly introduce one of our collaboration with industrial sectors, uh, with Pesonen, on the effect of design optimization and material selection on the fracture and fatigue performance of an industrial component. In this case, it's a crank arm as a component from a bicycle structure. So such studies are in coherence with the overall scope of our university, which is dedicated to more sustainable future and clean energy, water, and air. We believe that via this kind of optimization and increasing the strength-weight ratios in industrial component, it's possible to decrease the material waste and energy consumption in industrial sectors. And before getting into the case study, let me briefly discuss about the capabilities of additive manufacturing as a review. So additive manufacturing, in contrast to our traditional manufacturing technologies, it relies on addition of layer by layer of the raw materials. So unlike, for example, machining, that we have to deal with the bulk of solid material and remove excessive materials from the bulk to reach to the final product. In additive manufacturing, we start from the scratch and locally add the required material to fabricate the final form. So that's the way to save a lot of raw material and decrease the material waste as much as possible. But these layer-wise manufacturing techniques provide us with some unprecedented possibilities. And one of the most important is the possibility to have higher design and manufacturing freedom. So as a result, for example, from our previous studies, we managed to fabricate hollow sections that are shown here, for example, their designs. So in traditional manufacturing, for example, the first three designs, these hexagonal cells, were absolutely possible, and they are currently used for industrial applications. Via additive manufacturing, it's possible to also produce these hollow sections, for example, with diamond cells and triangular cells. These two also might be possible to be fabricated by traditional manufacturing, but it's very arduous. But the final design, you see here, the diamond-shaped cells and with a curved additional wall to increase the bending moment and make the structure stronger is only possible with additive manufacturing. So before using additive manufacturing in fabrication, such designs didn't exist, they were just concepts and conceptual ideas. And why is this important? Because such changes change also the stress flow in these kind of components, the points that cause stress concentrations, failure modes, and failure locations, and ultimately results in the final performance of these components under various loading scenarios, from high-speed impact loads to quasi-static compression or tensile loads. So such changes can make huge differences in the overall performance of our industrial components. And now, thanks to additive manufacturing, we can make modifications that were not possible before. So the importance of design freedom in additive manufacturing is totally established in these concepts. And however, nowadays, with our collaborations with industrial sectors, we have a chance to work with actual industrial components, or at least components that are used in practice. So in this case study, we chose a simple component, a crank arm from a bicycle. It was chosen by our industrial partner. You see the traditional component in action here. And of course, you see the big problem with our traditional components. They are very prone to fatigue crack in their fixed areas. So the initial design was defined here, and via optimization, this kind of design was proposed by the optimization software. The building direction or 3D printed direction was chosen along the axis of the component, and the fatigue assembly was decided to be like this to match the actual application of the component in action. Three different metal powders were chosen to fabricate the optimized components, and these three are commercially available and almost most frequently powders in industrial sections. First, titanium 64 or titanium vanadium molybdenum, titanium aluminum vanadium alloy. Second, aluminum 2139, heat treatable aluminum copper alloy. And last, the most famous and popular alloy in the history of 3D printing, stainless steel 316L. I think it has the longest history of being, I think it's the it's the metal powder that is being 3D printed for the longest time now. If we exclude 304, that is not used nowadays anymore. So the idea was to define a problem that can be fabricated in a maximum number of industrial sections and workshops. So the assumptions of the research were, as I said, the optimization domain from this design to this design was defined first by volumetric limitations, and after that, the material and component define a stern value. The 3D printing or additive manufacturing direction was normal to minimize the requirement of support structures. Then we used laser powder bed fusion as the most frequently used additive manufacturing technology. We use commercially available materials, and we use recommended optimized parameter to process these powders. So the material properties are excluded from this research. The first assumption is that all the materials are in their best performance, and anything related to failure is from the component and the manufacturer structure. We decided to use the titanium powder as the strongest material in its as-built surface. However, the aluminum and steel were shot blasted to have a better surface quality. As the analysis, we decided to use defect distribution, finite element analysis, surface quality measurements, and last fatigue test and factorography to analyze the performance of our components. So here you see the workflow from the initial design to the design optimization and manufacturing of the optimized component, and of course the partial machining and shot blasting. And first, from the microstructural perspective, we wanted to make sure that materials are in their normal conditions. So we analyzed all three microstructures, and nothing out of ordinary was expected, as we wanted to be that way. Stainless steel was in its austenitic form with epitaxial growth and those cellular subgreen structure. Aluminum has its own FCC background phase with, of course, the porosity content was relatively higher, but still below 1%, and titanium had the sequential alpha beta structure in its normal form. Of course, the titanium also showed this rare presence of titanium silicon carbides, which were excluded from the analysis because the presence was not that dominant. Next, we did the defect distribution evaluation and realized that the defects, although they seem to be a frequent defect, especially in the aluminum component, but the size of the defects were less than 200 square micrometer, and the circularity index of them, almost all of them was higher than 0.5. So technically, all of these are porosities with a size range lower than 200 square micrometers. From literature perspective, these can be seen as harmless flows inside the 3D printed metals that are very frequent, and they don't expect they are not expected to cause any kind of drastic fracture in the components. And as we expected, the surface quality of the shot blasted components were relatively better than the as-built condition. And in the case of titanium, in addition to higher surface roughness values, I think the most important parameter was the presence of these blue spots as valleys on the surface. These can act as drastic stress risers on the surface, and they are not that much dominant in other components. And now we reached the most important part of the research, the fatigue test itself. Before that, there was a finite element analysis run on the components to identify their points with higher stress concentration factors or hotspots that are prone and identified as possible failure sites. We wanted to know what to expect when at the end of the test. And then after that, we started our fatigue test analysis based on the global force and life cycles. And as you can see here, the results show that the stainless steel had the best performance. Next, when we consider the global force, it's aluminum, and last is the titanium one. And I think the most, because such fatigue test results contradicts the strength values of these raw materials. However, I think it shows the dominant effect of the, first of all, these spots with high stress concentration factors in the components, and second, the importance of surface condition on the failure of such components. In an attempt to make the results more comparable, the global force values were transformed into local stress values via finite element analysis, and the fatigue life curves were redrawn. As you can see, if we consider these criteria, the performance of the titanium is relatively better than aluminum. Here, this might be contributed to the better strain values of titanium, but still the 316L is the superior material to manufacture this component. And if we consider the fracture surface analysis, all the failures initiated from the surface, even for the aluminum alloy, although it has these porosities and clusters close to the surface, the local imperfection on the surface initiated the fatigue failure. And even in one sample of titanium that was shot blasted, these deep valleys initiated the failure. However, the comparison between the performance of these three classes shouldn't be that simple. We also should consider the strength to weight ratio. 316L has the best fatigue performance, but its weight is double the other components. So the problem with these kind of industrial case studies is that it's very difficult to standardize such comparisons, but the actual results are the ultimate outcome sometimes. So as on concluding remarks, we can say the results showed that the fatigue performance doesn't solely rely on the strain of the material. Parameters such as surface condition are more determining, at least in this case study. Design details, defects, and surface quality must be also considered in these consideration and comparisons, and local stress concentrations should be considered as an ultimate factor. And for the sake of comparison, we should also always consider the strength to weight ratios. And from industrial application perspective, we also have to consider the price of these materials. Titanium had a good performance, but it's very more expensive than 316L, for example. So these are different aspects to make these kind of results in actual applications comparable. Thank you for attention.